Okay, so this is going to be our second discussion of functional analysis. Today we are going to be talking about linear functionals and a few properties of them. Now, this won't be as long as the last talk, but I just wanted to see if people were actually interested. There's going to be another talk on quantum information theory going along with this, which is for one of my independent studies at UNH. Okay, so we're going to talk about linear functionals. Now we have a proposition. So let rho be a linear functional. Let V naught, a subset of the subspace of the vector space V, be the null space. V naught equals set V in V such that rho V equals 0. Okay. Now, if phi is a linear functional, vanishing on V naught, then phi is some scalar times rho, where A is in K. Now, it is possible that phi is the zero linear functional, and so A is 0. Conversely, let V naught be a linear subspace of codimension 1. That means the dimension over K of V mod V naught equals 1, which is the exact case we have with the null space of a non-zero linear functional. Then V naught is the null space of a linear functional. What this means is you can characterize linear functionals by their null space. More is true, and this surprises me. Let rho I equal 1 to n, be a set of linear functionals. So we have some nice linear functionals. And suppose the null space of some linear functional phi contains the intersection I equal 1 to n of the null space of these rows. So you have containment on their null spaces. Then phi is a linear product of these row i's. So there is some sum of ai's in the k, i.e. there exists some set ai in k, your field, such that phi equals the sum ai rho I. I just think that's pretty nifty. Seems a little too weak, but it's true. Now, first, we will actually prove this converse. And how will we do that? Let V naught be a subspace of V of codimension 1. Okay? Let little v naught be an element of V minus big V naught. So you're taking some element not in this. Then the set alpha times V naught plus V naught as alpha ranges over your k equals your entire vector space. You know this because V naught is codimension 1. Okay. So we know let V be an element of V. There exists a unique there exists at least an alpha, an element of k, where V times alpha where V is an element of alpha V naught plus V naught. Again, your codimension 1 at work. Okay, so suppose you had some beta. Suppose V is an element of beta V naught plus V naught. Right? Then 0 is an element of beta V naught plus V naught minus alpha V naught plus V naught. So I can move this over here. This is going to equal beta minus alpha of V naught. And V naught minus V naught is just V naught. It's a linear space. Okay, so that means beta minus alpha V naught is 0. Or V naught times beta minus alpha is actually in V naught. This is if and only if beta equals alpha. So we know this alpha up here was unique. Okay? Now we want to show linearity. Let V and W be an element of V. Then we're going to find there exists alpha and beta where V equals alpha V naught plus V naught, and W equals beta V naught plus V naught. So we're going to add them. Well, not really equals. We should be more careful, and this is actually element. We get V plus W is an element, alpha V naught plus V naught plus beta V naught plus V naught. Well, addition is always commutative. So this just equals alpha plus beta and V naught. And as we know, V naught plus V naught is just V naught. So we see phi of V plus W. So if we go here and we let phi of V equal alpha and phi of W equal beta, phi of V plus W equals alpha plus beta. We're just looking at what orbit it's in. Okay? That gives us the addition. I'm going to erase this, and if you want, you can come back and look at it. Now, let's take our own alpha. We're going to still let V equal alpha V naught plus V naught. And we're going to take beta, an element of K. Not that beta. New beta. Just any random element in K. Okay? We know that beta times V equals, V is an element, beta times V is an element of beta V naught plus V naught. Okay? Alpha. V naught plus V naught. Here we just multiply this side by beta and this side by beta. This equals beta alpha V naught plus beta V naught. It's a ring, so multiplication works. Multiplication distributes. But V naught is a vector space. So this is beta alpha V naught plus V naught. Okay? So we get phi of V, that equals alpha, phi of beta V equals beta alpha. So we get phi is additive here, and we can pull scalars out. So we get, it's a linear functional. It's actually linear. And the functional just means it goes into the scalar field. Okay. Next, let's erase the board so we have some space. First, we have some linear functional row. So let it be a linear functional. And suppose phi vanishes on the null space of rho. Okay? Let's take one element not in the null space. Let V be an element of a vector space minus the null space of rho. Okay? Now, we know rho of V does not equal 0. This is going to equal some scalar times phi of V. And we are going to look at the linear functional sigma, which is going to equal sigma, which is going to be rho minus a phi of V. Well, we know phi is 0 on the null space of rho. So for all V, an element of the null space of rho, sigma of V equals rho of V minus a phi of V, which is 0 minus 0, which is 0. That's nice. Okay, so next, take x, not an element of the null space of rho. Well, we know that this is codimension 1. So x equals some alpha times v plus v0, where alpha is in K and v0 is an element of the null space of rho. Okay? So we compute sigma of x equals rho of x minus phi minus a phi of x. This equals rho alpha v plus v naught minus a alpha v plus v naught. Okay. This equals, now these are linear functionals. It's going to equal alpha rho v plus rho v naught minus v. A alpha phi v plus phi v naught. Well, v naught in null space. Null space. This equals alpha rho of v minus null space, so this goes to 0. A alpha phi v. V naught's the null space of rho, so it's the null space of v. So this is 0. This equals alpha. Now I'm going to pull alpha out. We're working in a nice ring. Rho v minus phi v. A phi v. Well, that's 0. So this is 0. So we get sigma is the 0. Or rho of x equals a phi of x. For all x in our vector space. Okay? Now, here we have two linear functionals. What if we have more than two? We're going to use induction. We just proved our base case. Here's what we're going to do. First, our inductive hypothesis is for some n, an element of the natural numbers, for all n less than n, if the set rho I equals 1 to n plus 1, and phi are linear functionals. And the null space of phi contains the intersection I equals 1. That should be n, not plus 1, to n of the null space of rho i's, then phi is a linear combination of our rho i's. Okay? So what does this mean if n is 1? This means that the null space of phi, so phi vanishes on the null space of rho 1. Phi is a linear combination of rho 1. That's exactly what we just proved. So we can continue on. We're going to assume our inductive hypothesis. But now, let n equal n plus 1. We go 1 over what we know is true. Then we're going to have our set rho I equal 1 to n plus 1 and phi. Okay. Let v naught, a subset of v naught equal the null space of these rho i's. Okay, we're going to define rho I twiddle to equal rho I restricted to V naught. So we're only going to look at rho i's on V naught. Then the intersection of the null space I equal 1 to n, this is big N, of our rho i's, twiddle, is going to be equal the intersection I equal 1 to n of the null space of the rho i's. Intersect the null space of rho n plus 1. But we know this is contained in the null space of phi. Let phi twiddle equal phi restricted to V naught. So this also contained in the null space of phi twiddle. So we're just looking at this subspace. Well, I equal 1 to n fits our inductive hypothesis perfectly. So we get, so there exists a set AI in K where the sum AI rho I twiddle equals phi twiddle. So next, let sigma equal phi minus the sum AI rho I twiddle minus not twiddle. Okay, we know for anything in this null space, this is 0. So sigma so we get there exists some AI where get some alpha times sigma sigma vanishes on the null space of rho n plus 1. So there exists some AI plus 1, which is a n plus 1 in K, where sigma equals a n plus 1 row n plus 1. Now let's write this a n plus 1 row n plus 1 equals, well, sigma is phi minus the sum ai row I equals 1 to n. Okay? I can add. So the sum I equal 1 to n plus 1, get all of them, row n plus 1, equals phi. And we are done. Okay, and this is going to be our main proposition. Let's say a few definitions, and then we'll be done. Okay, now let V be a vector space. Over K. Remember, either complex numbers, the real numbers. Let X be a subset of V. Not a subspace, just some subset. Now we're going to define a complex, say convex combination as a set xi, a subset of x, and ai, a subset of open 0, close 1. Let's say I equal 1 to n, I equal 1 to n, where the sum of ai, I equal 1 to n, equals 1. So we know ai has to be greater than. So we know I has to be, we know n has to be greater than 0. And we know 1, if it occurs, then n equals 1. The sum, the convex combination is the sum ai, xi, I equal 1 to n. Okay. We're going to say, define X as convex if every convex combination of X lives in X. So, if we have xi, I equals 1 to n, a subset of x, any subset, and ai, I equal 1 to n, a subset of open 0, 1, where the sum of ai, xi, I equal 1 to n, the sum ai equals 1, then the sum ai, xi is still an element of x. Now this ranges over all ai's, all n's, where you have this set. Currently, as a simplification, we can assume these xi's are unique. But we can do better than that. Suppose we have our set ai, I equal 1 to n, a subset of x, a subset of 0, 1. And we have our xi's, I equal 1 to n, a subset of x. Then, let b1 equal a1. y1 equal x1. Let b2 equal the sum of ai's, I equal 2 to n. So suppose n is greater than or equal to 2. And y2 equals b2 inverse sum ai xi I equal 2 to n. Then let's look. We see y2 equals b2 inverse the sum I equal 2 to n ai xi. Okay? This equals the sum of b2 inverse ai. Now remember, b2 is a real number between 0 and 1. 0 exclusive, 1 inclusive. Okay, we also see sum I equal 2 to n, b2 inverse ai. This equals, as we showed, b2 ai, I equal 2 to n, inverse. Now this is a non-zero real number between 0 and 1. This is the sum ai, I equal 2 to n, over b2, which is the sum I equal 2 to n, ai, over the sum ai, I equal 2 to n. That's just one. So y2 is a convex combination of elements in x. So, if x is convex, y2 is also in x. If x is convex, y2 is still in x. Okay? And we see the sum I equal 1 to n ai xi equals sum I equal 1 to n a1 x1 plus the sum I equals 2 to n ai xi. We can rewrite this is going to be b1 x1 b1 y1 plus I'm going to do b2 inverse times, well, b2 times b2 inverse sum ai xi. Okay? This is b1, y1 plus b2. This right here is just y2. Now since b1 plus b2 is just the sum of the ai's, we get this is a convex combination of elements in X. So really, X is convex if and only if for A, an element of 0, 1, x1, x2, an element of X, A, x1 plus 1 minus A, x2 is still an element in X. We only needed to consider two elements. Okay. Next, we're going to have one more way of viewing this. Let A1, A2 be a subset of R greater than or equal to 0 with either A1 or A2 not 0. You'll see why I want that. We see A1 if Y is convex, then A1 plus A2 inverse A1 Y plus A2Y equals A1 plus A2. This is why I wanted one of them not 0, so this is division's fine. Plus A2, A1 plus A2Y. Now, this plus this is 1. So this is just Y. So we get A1Y plus A2Y equals A1 plus A2Y. Okay? Next, suppose A1Y plus A2Y equals A1 plus A2Y. As we saw before, Y equals A1 plus A2, Y plus A2, A1 plus A2Y. So we get Y is just all the convex combinations, i.e. Y A1 plus A2Y equals A1Y plus A2Y if and only if Y is convex. Okay. There's always more to erase. Next, let x be a subset of our vector space, and we're going to define the convex hull of x to equal the set a x1 plus 1 minus a x2, where a is an element of 0, 1, and x1, comma x2 are elements of x. So, all convex combinations. Next. Well, it's going to be easier. Have the convex of x, convex hull of x be the set of all convex combinations. Of elements of x. Wasn't right before. So, let y1 and y2 be elements of what we're going to call right now CO of x. And a be an element of 0, 1. So, y1 is an element of convex, is an element of CO of x. So y1 is going to equal the sum ai xi I equal 1 to n. y2 is going to equal the sum bi xi bi zi I equal 1 to m, where the set xi I equal 1 to n, zi I equal 1 to m are contained in x, and the sum of ai, I equal 1 to n, equals the sum of I equal 1 to m, bi equals 1. Okay, then a y1 plus 1 minus a y2 is going to equal the sum ai xi plus the sum b 1 minus a bi zi I equal 1 to n. Where the sum I equal 1 to n of ai plus the sum 1 minus a bi I equal 1 to m equals a sum I equal 1 to n, ai plus 1 minus a sum of the bi's. This is 1 and this is 1, so this is a plus 1 minus a, which is just 1. Therefore, CO of x is convex. Namely, by definition, it's the smallest convex set containing x. This is going to be very important. We call it the convex hull of x. Okay? So, that's all we're going to cover for today. Next time we'll talk about hyperplanes and talk about the famous Hahn-Banach theorems. I hope you've enjoyed today.